Welcome to the MR Physics class. I am Graham Mason. Today we will talk about several aspects that are related to the processing and interpretation of MR data. Fourier transform, the first topic, is used in a variety of applications for NMR. And also for many other fields. A concept called phasing is generally thought of most often with an MR spectroscopy, MRS, but it does have applications in imaging. Here today we will focus on the way that you would go about using phasing for spectroscopic studies. And the last term is related primarily to MR spectroscopy again, chemical shift referencing. Professor de Graaf has discussed this previously. We will discuss it again today. So with Fourier transform, the goal is to help us go from a raw signal to something that we can interpret more easily. Our raw data, the data that come directly from the scanners, from the magnetization that's precessing in the XY plane after we do an excitation. For spectroscopy, would look something like this. The raw signal that comes to us, caused by the precession of the net magnetization in the XY plane in the vicinity of our conductor, our detector, will look something like this. Here we have an amplitude of signal versus time. And the signal dies away over time according to T2, T2 star, and the net magnetization dephasing in the XY plane decreases our signal. And there's a general decay that looks in the middle of this, kind of an average that looks smooth, and that would reflect something that is at or very close to the Larmor frequency, so right in the rotating frame. And then there are a lot of oscillations, but those make clear that something is outside, something is oscillating at least slightly differently from our main frequency, called the carrier frequency. So if we do a Fourier transform of that signal, we find, oh yes, there is a water signal. I'll discuss, later I'll explain how we know this is at 4.7, how we know that that's water, how we know what these other signals are at 2 and 3 ppm. But there are chemicals in the sample that contain N-acetyl-aspartate, creatine, and choline, and there's a lot of water which we take great pains to suppress, but rarely can suppress entirely. And together, the chemicals with these frequencies give us this spectrum. Now, remember that parts per million refers to frequency, hertz per million hertz. So it's a frequency divided by the Larmor frequency of separation, and then reference to some particular standard that Robin de Graaf mentioned, and we will discuss again. Now, in this case, it's common in MR experiments, the Larmor frequency, the carrier frequency, has been set exactly on water. So that means this had anything with this particular frequency will appear to be stationary in our rotating frame. These things have other frequencies. They can be a few hundred hertz away from here, so they will precess and oscillate relative to our reference. So this average behavior is coming from the residual water that we did not succeed in entirely suppressing, and these other oscillations come from this. Now, very few people would be able to look at this signal and tell you what frequencies comprise it. This spectrum on the right came by doing a Fourier transformation of this. Joseph Fourier A Frenchman in the late 1700s, early 1800s, proposed that every function can be expressed as a series of sinusoidal cycles. A function can be something that we think of just mathematically. It can also be shapes, surfaces, anything that can be expressed in terms of numbers can be is some kind of function, and that can be expressed as a series of sinusoidal cycles. Fourier himself was pretty interesting. Um, he actually was imprisoned during the terror following the revolution in France, but he was released after not long, and eventually he served in the army under Napoleon, and he played important roles in that regard. Um, what he developed was very helpful to us. So MR signals are composed of frequencies, and they're based on the rate of precession of each component of the sample. The precession are relative to the Larmor frequency. So if we had a sample that with a component, some signal that was exactly 4 hertz away from our rotating frame reference, it would look like this. These are sinusoidal curves, and you can tell the frequency by measuring. Say, well, one way to do it is there are, as I can see, that's 1 second, and that second contains, okay, here's 1 cycle, here's another complete cycle, and now it's repeating again. There's 3 and 4. So 4 cycles per second, that is 4 hertz. You could also measure the distance from this peak to that peak and calculate down here. This is 0.25 seconds. So 1 cycle in 0.25 seconds, that's 1 cycle divided by 0.25, has a value of 4 hertz again. If we want to express that as a frequency, we would say, oh, okay, here's some frequency axis, and right here at 4 hertz, there's a spike. That represents our curve. Really, our NMR signals don't look like that. They don't look like this either, but this is a little closer. Actually, our NMR frequencies have many signals. It's a mixture, a hodgepodge, and it would be difficult to look at this and tell for sure where the cycle repetition are. It looks like maybe something's happening here and here, but it's a little different in these other places. So what do we get? So we'll do a Fourier transform to figure that out. This is, as I want to point out, these figures were made by Robin de Graaf. Now, first we're going to start with a cosine function. Remember, a sine and a cosine are the same thing, except one is relative to the other. It's rotated by 90 degrees. You could think of them that way. A sinusoidal wave starts at 0. A cosinusoidal wave starts at 1. Now, we're going to do a simple, just a cosine transform. This is our observed signal, and we're going to test it against some signal that we want to know if it's maybe forms part of the spectrum. So if we take this signal and multiply it by our test signal, it can oscillate between 1 and -1, for example. What matters here is it's exactly this particular frequency. And look, they happen to be the same, so our initial guess in this case is correct. If you multiply point by point this function by the test function, you get numbers that are all either greater than or equal to 0. So this is 0.0. You have plus the maximum here, you multiply it by +1, you get a positive number. If we go down here, we have a negative number on the amplitude. We multiply it by -1, we get a positive number. You multiply 2 negatives, you get a positive. In here, there's a 0 crossing. So 0 times 0 gives you 0. There's no way for this product to be less than 0. The sum, if you integrate over the whole signal and add up the results, the sum will always be greater than 0 if you have if you have guessed the right resonance frequency. Now let's test an incorrect frequency. So here's our original signal, and we're going to test something with it. See how there are more oscillations? This is oscillating higher. We have a signal it has 4 complete cycles, so it's 4 hertz here. And this one has 1, 2, 3, 4, 5, 6, 7 and a half cycles. Now the integral of this product actually comes out to be 0. The reason now here we have our initial signal, our signal, and there's a test. Well, they both match. That's 1, so that's fine. Now we go down here. This is our negative amplitude signal. If we trace this down here, it's also negative, but it's not. They don't match at the bottom. It's somewhere here, and in between we have other signals. So if you end up multiplying each point by point with this, sometimes the product is positive, sometimes the product is negative, and if you carry this out to infinity, you get 0 for the sum of all of those test points. Now here we have another test, also wrong. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hertz. That's 10 cycles per second. So 10 hertz multiplied by our product, by our original signal, gives this. So again, if you add up all of these points, and if you take the area under the curve, basically, and then it comes out to be 0. Okay, to put this procedure into equation form, we use a cosine function. This may be something you could program. We start with our sample signal, which is a cosine function. You remember they start at 1 and they follow very regularly up and down. So this is our this is our NMR signal for this thought experiment. And cosine 2 pi nt, those are our test signals. This dot product means we are multiplying each time point together to get our result. So whenever, as we've just showed in that graph, when n equals m, so the frequencies match, the integral is greater than 0. When m is not equal to n, the integral equals 0. So that means we get a spike at that frequency. To make this even more general, though, because m and n don't have to be exact, very precise integers. We can use an integral calculus. And now here, instead of cosine 2 pi mt, we're saying, well, we have a general function. It could be anything. And we're going to test that by multiplying it by a whole range of frequencies, new. Could be any frequency. All right, so now let's carry out that procedure. We do this cosine transform. And here we are. We have multiple frequencies that comprise the signal. And see that there are 6 peaks here. Something you may notice that seems a little odd is that what's on the right is a mirror image of what's on the left. And that's going to introduce kind of a strange concept. See, we have positive frequencies on the right and negative frequencies on the left. I mean, who ever heard of a negative frequency? When you turn on your radio, you set it to maybe 90.5 megahertz around here, or 107.9 megahertz, depending what kind of music you like. And you don't have negative frequencies available on your radio dial. That's because we have this rotating frame concept. You can have some magnetization that precesses clockwise and some that precesses counterclockwise, because its actual frequency precession is a little bit faster or a little bit slower than the Larmor frequency. So this frequency axis is actually frequency relative to what we call the carrier frequency, or or the Larmor frequency, this rotating frame. The reason it exists, that these mirror images exist, is that all we have is one trace. We can't tell if this trace came from something that's rotating clockwise or counterclockwise. Here's why. Suppose you have this case up at the top. We have this ball. We know from this perspective that it's going clockwise in the XY plane. Now, if we look on the left, imagine we were able to take a view of this circle on the right, exactly on the edge. You're right on the edge. We have no view, we can't see anything up or above or below. Well, all we would see would be this ball going back and forth. Now, suppose we have a ball going counterclockwise and we look at it exactly edge on. Again, we can't tell anything about it. We just see the ball go back and forth and back and forth. And on the left, these perspectives are what have been, that they are equivalent to this. We are watching XY magnetization precess in the XY plane, but only with the vantage point of the very edge. We can't see whether things are precessing clockwise or counterclockwise. We just know that the signal amplitude is going up and down. Okay, so here we go. Now if we were able to change our perspective and look straight down on the XY plane, now we would be able to tell that the magnetization was rotating clockwise. Or this other, let's go counterclockwise, where there's slightly negative, lower frequency, so a negative frequency in our spectrum, lower than our carrier frequency, we could tell. We could look straight down on it and see moving counterclockwise. And our ability to do this clockwise or counterclockwise distinction is from something called quadrature detection. That'll be explained later in Dr. DeGraff's hardware lecture. Once we know that, then we are able to, we have something precessing clockwise or something precessing counterclockwise, we're able to tell. So on the left, we have a ball going clockwise. And now when we start at 0, it's got a value of 1 in Y. Here we are. And it has a value of 0 in X. There we are. As it goes around, it will reach a value of 1 in X and 0 in Y. So there's the 1 in X at the same moment that Y reaches a 0. And negative Y and 0 for X. Here we are. So we can, if you follow this graph and imagine where the ball is at each point in the graph, you get this circular rotation clockwise. If we go to the other side, we have now a counterclockwise rotation. Look at this graph. We start with 0x and 1 in y, just the same as what's on the left. But now we go to a negative value on x. Yes, it's on top of the graph, but imagine positive goes toward where the letter is located on the axis. So we have a negative x value at the same time we hit a 0 crossing on y. You can go through this graph also, look at each point on the x and the y, and you'll find that you can tell that this ball is going counterclockwise. So this is quadrature detection. Now, we talk about the xy plane, we talk about x magnetization, y magnetization, but you're also going to hear a lot in MR about real and imaginary. So these are, we could also call these the real and the imaginary axes. Which is arbitrary. But the point is that we have to be able to keep track of where the magnetization is in this real imaginary plane, this XY plane, to know if the frequencies we want to see are a little bit higher than our Larmor frequency or a little bit lower than our Larmor frequency, our rotating frame. You may hear terms, you may show up one day and find, oh, you can't run your experiment. I'm sorry, there's a problem with the real channel. Um, uh, there's a problem with the quadrature detection. When the quadrature detection goes out, we don't get a perfectly overhead view of the XY view. If it's a little bit off of adjustment, then it's as if we are looking at this circle from a slight angle, and that introduces a very slight ambiguity in whether things are positive or negative. And in the spectrum, what you'll see is your primary peak where you know things belong, and then on the opposite side of your carrier frequency, you'll see a very small peak, at the mirror location. That's because the quadrature detection is out of adjustment. It's rare that that happens, but if you'll hear about real and imaginary channels, and you're going to hear about quadrature detection. Okay, so now we get away from just a pure cosine transformation, and we go to the Fourier transform. That includes real and imaginary components, which by what we mean is they're cosine and sine components mixed. Now, instead of saying x cosine and y sine or vice versa, we call this the real component, and this imaginary number, it means it's actually the square root of -1. This I represents the sine component. A purely sinusoidal signal, so this is some function that we want to analyze. In this case, it's a purely sinusoidal type signal. It has a frequency nu sub 0, we call that, because that's the center of it's wherever the center of the peak is. We have a cosine component, we have a sine component, and you can look it up in a book or if you want, or you can take my word for it, that the sine and cosine combination with an imaginary sign is equivalent to the e, as in natural log, the e raised to the I times 2 pi frequency times time. So if we carry out this operation, we take our function and we multiply it by this component, which could also be expressed as cosine and sine if you want it, negative sign. That translates into this expression. An exponential times another exponential allows you to add the exponentials together. And just as if for the cosine function, when the frequencies match, that is when this term collapses to 0, the integral of this is greater than 0. When the frequencies do not match, the integral is equal to 0. Now, the frequencies that I showed you before in the transforms were spikes. There were straight lines assigned at particular discrete frequencies. If you have seen NMR spectra, maybe through your work here or through a lab when you were in graduate school or college, you'll see that you'll know that those peaks aren't actually single frequency spikes. They have a width. They have a shape. The reason they have a shape and the reason they have a width is that we don't have a purely infinite sinusoidal curve or a mixture of curves. We actually have T2 or T2 star decay. So our function is not just this component, which is the sinusoid that I showed you, with the amplitude starting at time 0 of m0. The whole thing is decaying with the T2, governed by T2 as the signal dephases. And this is why the transform gives you some width. Okay, if you multiply this original signal by a test function of 2 pi 5t, cosine 2 pi 5t, you get this function. It looks like the frequencies have been matched exactly. Now here is a graph of the amplitude you get testing every possible frequency plus and minus 20 hertz. And in this case, we have matched the frequency exactly, so it's at the highest amplitude. This is where you find the highest amplitude of the peak. The peak center is the location of the frequency of that peak. Now, if we go off a little bit, the integral of this doesn't go to zero because there's some positive and there's some negative before the signal, but eventually the signal dies away. So 2 pi times 7.5t is not quite a match. But overall, if you add up the areas of the positive part and the areas of the negative part, you come up with a net positive for this curve. So here we are on the shoulder of the peak. If you go farther off resonance, now we get more positive and negative dips before the signal dies away, and there's more opportunity for the negative and the positive to cancel each other. And you can imagine if you go farther out, there's still more opportunity, and very quickly the integral of this peak, where the positive and negative components cancel one another out. Let's go back to the calculus form, the continuous function. Here is our sample function. We have the biggest we have is at the initial time, m0, that's the full net magnetization processing in the xy plane. Here's the sinusoidal oscillation in case we are a little bit off resonance. If nu equals 0, you just see no oscillations. And now there is a relaxation, a transverse relaxation term. So if our signal doesn't start at minus infinity, we open the receiver and this signal starts at time 0 and goes to infinity if we could leave the receiver open that long, and if we had some signal persisting that long. So here's the original function. We're going to do a Fourier transform on it. When we put those together, here is what the full function looks like. And we're going to make a change now too. This is nu, but nu is frequency, cycles per second, or hertz, or megahertz. Here, omega is also a frequency, and people may use them interchangeably when they speak, but actually omega by convention is 2 pi times nu. So nu is cycles per second, and omega is radians per second. So 2 pi is how many radians are in one cycle. You could also think of this 2 pi, this means 360 degrees. But we work in radians instead of degrees. So our Fourier transform is going to take the original signal, which is a function of time, and turn it into a frequency. The original signal, as we've already discussed, has a real and imaginary component. Likewise, the Fourier transform has a real and imaginary component. The real component is called absorptive, and the imaginary component is called dispersive. And normally we don't look at this when we're analyzing our data, the dispersive component. It's much harder to interpret. The little I here represents that's the imaginary component of this. So the absorptive component, that's A, as a function of frequency. So this is looking across a range of frequencies presented in radians. That's equal to this expression. So M0 is the net magnetization, T2 is the transverse relaxation constant. So this component doesn't change. This numerator does not change as you go across the frequency spread. The denominator, though, there's 1 plus omega 0 minus omega. Now, omega 0 is the center of the peak in question. Could be the center of the water peak, could be the center of the Cretan peak, or any other peak. M0 is some peak, the location of some peak, and omega is where in the spectrum we happen to be looking, what frequency location. So if we're looking right at the center when we do this calculation, omega equals omega 0, then the one number minus the same number gives you 0. So you have a 0 in this term. That means the whole term, 0 multiplied by T2, is still 0. And you get 1. That's 1 in the denominator. So the value of at the center of the peak is A equals M0 times T2. That is the biggest the amplitude of the absorptive component can ever be. Um, if you move a little bit away from from WZ, from omega 0, then this quantity grows. There's a bigger difference. You square it, it becomes positive and bigger still, and multiplied by T2 squared, and then the denominator begins to grow. When the denominator of a ratio grows, the ratio decreases. So as you move away from the center peak, the amplitude of the absorptive component falls. Now the dispersive component, the part I told you we don't generally look at, that has the same dependence of the denominator, but the numerator also now has a dependence, so it's going to have some other shape. Here is our original signal oscillating over time and decaying. We do a Fourier transform, and here are the absorptive and dispersive components graphed as a function of frequency. And remember, in a previous lecture, we said that the delta nu, that's the way people often express the peak width, the change in frequency, or the full width at half maximum, is equal to 1 over pi times T2. And you can go back to the equation for the absorptive component in the previous slide if you want, and either derive this equation explicitly or plug the formula into Excel and make this graph and just see which verify that this formula is correct. And you may see why we don't analyze the dispersive component generally. It's not as easy to quantify. Here we can measure the area of the peak pretty easily, or there are other approaches that we take to analyze spectra. This is not so straightforward. Now we look at a more general case. The real and imaginary components we've talked about have been very discrete. We called one absorptive and one dispersive. Now, imagine, however, that what actually happens is the XY magnetization the net magnetization is tipped into the XY plane, and it begins to precess. Everything takes some time. It takes a little bit of time for the radio frequency B1 to play out. There are tiny delays while switching occurs between transmission and receipt. There are different distances between different parts of the sample and the detector. And all of these things mean that if we tip into the XY plane, it's difficult to predict exactly where the magnetization will be in its location, whether X or Y or somewhere in between. That's called its phase. Where it lies in the XY plane is its phase. And here we have a spectrum, and these don't look like dispersive peaks or absorptive peaks. There's something in between. That's because the phase is not the ideal that we've discussed so far. Now, all the information exists for us to have a perspective that lets us see an absorptive component and a dispersive component. But the default that comes out of the scanner often does not look ideal. It looks more like this. So we want to redistribute the information between the computer, between the spectrometer's real and imaginary channels, so that we can look at what we really would call a real spectrum. And that is called phasing. That's our next topic for today. So the most common phasing is zero order phase, is a zero order phase correction. And that's the scenario that I described a moment ago, where the XY magnetization when the receiver opens is not aligned perfectly on the X or on the Y channel, on the real or the imaginary channel. It's somewhere in between, and we have a very hard time knowing in advance where that would be. So here was a real amplitude, here's the real trace, and here's the imaginary trace. And both of these actually do come out. In the hardware lecture, we'll explain why you get a real and imaginary trace, how the hardware gives us that. Well, instead of just the real trace we've been talking about, now we're talking about the real and the imaginary. And we want to see this phi is a phase, and sub C stands for correction. We want to take point by point the real and the imaginary components and move some of the amplitude from one and back to the other um, in a way. We use the same sort of redistribution at every time point to get the spectrum to look like an absorptive spectrum. So if we do a straight up Fourier transform, then we get the out of phase spectrum. If we add a phase correction, we can move some of the signal from the imaginary channel into the real channel, and we move some of the information from the real channel out into the imaginary channel, so that in the end we're looking at an absorptive spectrum. So we'll do that by basically, it's called a phase correction. This may be about 45 degrees. And here, once we apply those degrees, we can turn this into something that's much easier to interpret. Now, and a less common phase correction is first order. And that can happen for different reasons. Now, first order phase correction is a phase correction that instead of being constant across the frequency, the same phase applies, phase correction gets used for every single point across the frequency or every single time here. Now we have a time dependent, or we have a frequency dependence in the amount of phase. So how much phase correction is applied depends on what the frequency is. So now we have not just phi sub c, but c, the correction is a function of the frequency omega. This is an example of a spectrum with a first order phase deviation. When we apply the proper frequency selective phase, we can now we get back to the absorptive peak we want. One common place for this to happen is if there's a delay at the beginning of the acquisition. This happens when there's like a digital filter applied on our Brooker scanners. Another is if we have a spin echo, for example, and the echo times don't quite match. It's true, on the one hand, we don't get complete refocusing, but we can also get some strange phase behavior. And we can apply a first order phase correction to deal with that. And the last topic for today is chemical shift referencing, which Robin de Graaf has addressed in his initial lecture. So we'll talk first about where frequency differences come from in NMR spectra. Well, the biggest influence on frequency, remember, this all comes down to gamma times B0, that basic equation from the first lecture. Anything that changes B0, magnetic field strength, or anything that changes gamma, the identity of the nucleus, that will have a huge effect on the Larmor frequency, the frequency of precession of the nucleus. So for whatever magnetic field strength you're using, carbon-13 has a gyromagnetic ratio that's about 1/4 that of protons. So for any given magnet, carbon-13 will have a resonance frequency, a Larmor frequency, that is about 1/4 the frequency of protons. So for example, if we take a 42.6 or 42.57 megahertz multiplied by field strength, you look at different field strengths, you can see the magnetic, or you can see the resonance frequencies you get for each one. Something that I found interesting, practical terms, is we used to do experiments on a magnet whose carbon-13 frequency was right around public radio, and we liked to listen to the music. On our little magnet, every time we pulsed at the carbon-13 frequency, we also picked up a beep interspersed with the violins. So we were transmitting at a frequency very similar to what the radio the radio station that we were listening to. We'll get into that. Actually has some bearing on coil design and MR system design that we'll discuss later. But that's just an aside. The biggest influence on the resonance frequency, on the frequency of precession, is the nuclear identity and the magnetic field strength. Now, when we get into NMR spectroscopy, what allows us to do this, what really makes the NMR so powerful, is that the molecular identity also has an effect. So remember, anything that changes the value of B0 seen by the nucleus will affect the gamma B0, the Larmor frequency. So suppose you were to take a sample of water, put it in a 3 Tesla magnet and scan it. And then you were to put it inside a special box that blocked out most of the magnetic field, most of the B0, and put it back in the scanner. Assuming you could have such a special box safely in the scanner, you can imagine the B0 field of that water would be very low, even though it's sitting in a 3 Tesla scanner. And therefore the Larmor frequency would be very low. So for NMR spectroscopy, there's a less extreme but analogous situation. The electrons surrounding a nucleus shield it. They block out part of the main magnetic field. So if you have, instead of a special box, if you have a dense electron cloud surrounding a nucleus, you will block out part of the B0. And a lower B0 will result for that particular nucleus. And you'll see a smaller gamma B0. So we take here an example of glutamate, and we're going to look at the carbon resonance here. If we had carbon 13 in this molecule, we look here, and here's for glutamine. We'll look at the equivalent carbon. There's a carboxyl group here compared to what glutamine has, the nitrogen, the amino group here. Carboxyl groups have oxygen, and see the minus charge on there. The oxygen is very electrophilic. It has a vacancy in its electron shell. It tends to draw electrons to itself. Well, where could it get them? Here's a CH2 group with electrons surrounding it, and those electrons actually get pulled by the oxygens. They are much less likely to be found at any given instant around the carbon. They spend more time around the oxygen. This carbon nucleus is more exposed to the B0. See, it sees the full, something closer to the full magnetic field strength of whatever scanner you're using. If you look over here at glutamine, there is no carboxyl group. There's an oxygen, which will have some effect, but nothing like a carboxyl group. There is not the draw of the electron cloud away from this carbon, and therefore the electrons spend more time around the carbon, and they shield it. They block out the B0 to some extent. And so glutamine sees less B0 and has a lower gamma B0 than glutamate does at this carbon position. There's still some effect here at the next carbon, still residual effect there. And by the time you get to this carbon, there's still a little effect left, but not much. So the strongest effect is up here. And actually, there's a way, if we look at the carbon 5, I won't show you an example of this, but we look at the carbon 5, there's a pretty dramatic effect here. So what happens then is different molecules in different positions within those molecules respond with slightly different frequencies, and we can use those to quantify one chemical distinctly from others. And we can use that to look at what differences may occur within the molecule. So at 4 Tesla, carbon 13 glutamate responds, we say it responds with a Larmor frequency of 42.5 megahertz. But actually, all across the spectrum, different chemicals respond at slightly different values in that vicinity. So if we have a glutamate that's responding at 42,510,204 hertz, glutamine with a slightly lower B0 responds at 170 hertz less. So instead of 204, we have 34. And this is a very small fraction of the total. We'd still say they have a Larmor frequency of 42.5 megahertz. But this small distinction is enough that we can measure them separately. There's something else called J coupling that will be discussed later in the course, and that has to do with the interactions of different spins within a molecule. And we'll talk about that later. Okay, so when it comes to acquiring data, to observing glutamate separate from glutamine, or any two chemicals at different frequencies, we would put ourselves in the rotating frame for one of them and then look to see what's going on with the other one. So glutamate and glutamine precess at slightly different Larmor frequencies. So if we put ourselves exactly on resonance for one of them, we're going to see a slight rotation away from our perspective for the other one. When we do a Fourier transform of this, that corresponds to a slightly different location in that they have a different resonance frequency. So relative to our carrier, to our our nominal rotational frequency, they show up at different places in the spectrum. So this is a carbon-13 NMR spectrum from a human brain after we've given this person glucose that has carbon-13 in it. Glutamate, C4, is labeled very prominently. It's because their brain has a lot of glutamate in it, and a lot of the glutamate ends up with a carbon-13 located in it. Here's glutamine. There's less glutamine, but an appreciable amount of the glutamine also ends up with carbon-13. See, the frequency separation between these two is distinct. It's very easy to see them separately. And now glutamate carbon-3, that's the next carbons down the chain. They are still affected by the difference in the molecules, but it's not so strong. Then I mentioned to you that there's J coupling, something called J coupling, and that we will discuss later. That is splitting the peak here. For this glutamate carbon-4 peak has some interactions with other spins, and we end up with some little deviations here at the base of the peak. But for now, the main point here is that glutamate can be distinguished from glutamine based on the different chemical environment causing a different value of B0. Now, notice that the axis on there was parts per million. Now, Robin discussed that in the initial lecture. That's hertz per million hertz. That's why parts per million. The first time I submitted a paper in psychiatry, the reviews came back, and this reviewer was used to parts per million representing concentrations of things, like maybe the amount of some pollutant in the air could be measured in parts per million. In this case, it's, I explained it's something different, and the paper was accepted, and that was fine. In this case, we want to use it to help us understand each other. So the number of hertz difference in chemical shifts is proportional to the amount to B0. So that's because the frequency of precession of any given atom is equal to gamma times B0. If you change B0 by 10%, then gamma B0 changes by 10%. That means the differences between any two molecules will, relative to one another as a percentage, they're going to be the same. So at 2 Tesla, 2.1 Tesla, an old scanner we used to have, N-acetyl aspartate, a chemical commonly found in glutamatergic neurons, resides 260 hertz away from water, a lower frequency than water has. At 4 Tesla, it's 500 hertz away from water. Now, the Larmor frequency is, here it's about 80, at 2 Tesla, it's about 89 megahertz. Here it's 170 megahertz. If you figure out the Larmor frequencies for these two fields and divide 260 or 500 by the respective frequency, you'll find that they are, both cases, NAA lies 2.94 parts per million away from water. So that takes care of frequency differences. No matter what magnetic field strength you look, when you read a paper and you see a carbon-13 spectrum with glutamate and glutamine in it, they will be separated by a couple of parts per million. Now, exactly why is glutamate located at where you see it? Why is glutamate at 34.2 parts per million? Why is glutamine over here just at about 32 parts per million? So far, all we've talked about are frequency differences between things. But to make communication easier, I could say across laboratories, across tissues, across samples, we want some absolute whenever possible. So everyone has agreed to use DSS, or here's another trimethylsilyopropionate. Everyone agreed that in protons and in carbon-13 that would be called 0. That we would say that's the Larmor frequency. And everything else is referenced to that. So that turns out that water always sits around 4.7 parts per million away from TSP. Now that exactly where the shift is can depend on the temperature and the pH, but it's about, in vivo, it's about 4.7 ppm away from water. So here we come back to the spectrum. And now, once we set a particular standard, the TSP would be out beyond the view of the screen, of the slide. Everything else has a very particular location. And if someone in a lab 8 years from now at a magnetic field strength of 30 Tesla has a signal at 34.2 parts per million, you can see that signal and you can say that's probably glutamate they're talking about. Or glutamine would be over here. Now I say probably because once in a while you encounter two chemicals that resonate in the same place. But for the most part, for most of what we look at, that's not the case. There are a few cases that we take into account regularly. Now, something else that Robin mentioned, that is, it's an oddity. I've seen even experienced people forget this, get confused. So there are two things here that are strange. Notice that this graph on the right has lower numbers than on the left. Almost all presentations of spectra have these higher numbers on the left. And to make things even more confusing, that's downfield, even though the numbers are higher. And that's historic. So higher frequencies, I'll explain the history in a moment, but what you need to remember is higher frequencies follow the ppm. Higher frequencies are to the left, lower frequencies are to the right, but upfield and downfield, those are opposite. Now the reason is that it has to come down to shielding. As I mentioned, the electronic shielding. Glutamate, the carbon-13 here, has any carbon at this location has less shielding sigma, is the term for it, than for glutamine. Now we'll go for here to look at the original NMR studies were done with swept field. Currently, we transmit at the Larmor frequency. We transmit at, say, at 3 Tesla, 120 some megahertz. And it's not just one discrete frequency. We hit the sample with a band of frequencies centered around the Larmor frequency, the nominal Larmor frequency. So it may be where we hit the sample with, say, 127 megahertz plus or minus 10 kilohertz. Now, in the old times, there would be a constant frequency transmission, and the magnetic field was swept. It's called swept field. The magnetic field would be taken from a low value to a high value. If we have a sample with glutamate and glutamine in it, and we're transmitting at a constant frequency, the glutamate, remember, it's exposed to whatever magnetic field we apply. And as we dial up the magnetic field, the glutamate's going to resonate at the given frequency sooner because there's less protecting it. We have to increase the magnetic field even more to overcome the shielding that's surrounding the glutamine. So that's why we end up with a spike on the right at a higher magnetic field strength for glutamine. And that's why this is called upfield. Things that are shielded, you had to go up in the field as you swept to get a resonance. Things that were unshielded or less shielded would appear earlier for downfield as you swept the field. So now we do pulse and Fourier transform NMR. And there you have a constant magnetic field. It's 4 Tesla, 7 Tesla, or it's just 3 Tesla, and it stays there often for decades. That just stays constant. And when we apply a burst of radio frequency energy to tip the magnetization, and it responds. So now we have our signal amplitude, and our axis is no longer B0, our axis is frequency. For a constant magnetic field strength, the glutamate is more shielded, so it resonates at a higher frequency. Remember, these numbers on the left are bigger numbers, but they're presented, instead of flipping all the data around to keep things consistent with the original NMR experiments, we have our data presented this way: low field to high field, downfield to upfield, but higher frequencies, higher ppm appear on the left. So to summarize this, we acquire our MRS data as a series of amplitudes oscillating in some form over time. The length of time we can acquire is usually somewhere between tens of milliseconds to hundreds of milliseconds. We go out to some multiples of whatever the T2 value is, or the T2 star value is. So that whatever signal we observe, that represents the sum of whatever is coming from the mixture of chemicals in the sample. And for an image, that's mostly water, and all these other little chemicals like glutamate are also present, but they are so much less than water that for regular MRI we just don't see them. But for spectroscopy, we do. And to help facilitate the identification of these chemicals, we usually use spectral processing. There is actually some time domain processing, but that's separate. The spectral processing is a more common approach. And the most common approach of the spectral processing methods is Fourier transformation. Fourier transformation converts the time signal to a spectrum of frequencies that represent each chemical. So generally, the general thing to remember about a Fourier transform is it'll take whatever your x-axis is for your original signal, and it will give you something called a spectrum that is the inverse of that. So if we have seconds on our x-axis, we have 1 over seconds on our processed, on our transformed axis. Remember, 1 over seconds is hertz. That's frequency. For imaging, we acquire our data in time also, but there's a little, as I will explain in a later lecture, there's actually a scaling factor that gets applied. It converts that time of an image into something called k-space, or also called reciprocal space, or inverse space. It has units of 1 over centimeters, or 1 over millimeters, 1 over inches. When we do a Fourier transform of that 1 over distance axis of our time domain image signal becomes distance. So our raw signal has units of time, or 1 over millimeters. It becomes millimeters. This lecture focused mainly on spectroscopy, but the same principle applies in imaging. Now, so we also introduced the concept of positive and negative frequencies, which, as I stated, that's bizarre in regular life. But really, it's a matter of relative frequency. So we put ourselves in the rotating frame, and anything that moves to one side of you, moves away from you in one direction, would be called positive. Anything that moves in the other direction is called negative. And to get an unambiguous measurement of where they lie to the left or right of you, we need something called quadrature detection. Because then we can tell whether things are going clockwise or counterclockwise. The quadrature detection gives us something called complex data. It has real and imaginary components. Now you can also think of these as X and Y components. When you process a complex time domain signal, you also get a complex spectrum, and we mix the components of the real and imaginary, or the components of those spectra, to get something that is what we call absorptive. We want something that's more easy to quantify. Once we have a spectrum, the frequencies of each chemical are called their chemical shifts, because they're shifts because they are shifted somewhere on the spectrum axis relative to a reference. The chemical shifts are the deviations of each chemical's resonance from whatever the nominal Larmor frequency is. And that the reason that those shifts exist is because they have slight differences in Larmor frequency. Remember, Larmor frequency equals gamma times B0. So the molecular structure changes the B0 value slightly for each nucleus, each nucleus of particular atoms in each chemical, and that's due to the chemical structure. And now the assignments of the peaks are based on their frequency separations from one another. So that gives us why there are a certain number of parts per million separating different peaks. But the exact number that we've established that everyone accepts for any given chemical is relative to chemical standards that we've agreed about. Now, something that comes up in conversation sometimes, and history interests me a lot, is it like, how do we know? If we get a signal from the brain, how do we know that that signal corresponds to glutamate or to N-acetyl-aspartate or to lactate? And it is painstaking work. It's rare now that someone identifies a new chemical in vivo, but it does happen occasionally. The last one I'm aware of was MSM, found in the brain by Brian Ross. He identified it as this chemical that accumulates from people taking MSM as part of their glucosamine chondroitin supplements for arthritis. But what happens is you have to, when you see a signal at a particular location, you look at libraries. Now this used to be paper records of spectra for all kinds of chemicals kept in the chemistry library. Now you can find lots and lots of chemicals online in different databases. But you look up those chemicals with the ones you're suspicious that they might be, that we already know from other methods before NMR was used, that there's glutamate in the brain, for example. But you go looking for what might exist in the brain, try to find those chemicals. When you find what you think might be it, you buy or make some of that chemical, dissolve it in solution and measure that and make sure that it could still explain it. And then, if possible, you do make some kind of intervention or look for a disease where you know this chemical is altered, and you see, is this chemical enhanced, like in the disease? If you give a drug that blocks the breakdown of the chemical, is it actually what you're seeing? So Kevin Barr in the late 80s and early 90s was making the first measurements of GABA in the brain. And one of the interventions was to give a drug called vigabatrin, which blocks the breakdown of GABA. And the peak he believed was GABA rose as expected. And that was one of the steps he took to verify that what he was measuring actually was GABA. So it's time-consuming, painstaking work, but it's worth it once it's well established. Then everybody can refer to that peak. They know what it's supposed to look like, and they know it belongs. That concludes this lecture for the NMR physics course.